we've got a function here, a quotient in fact, and we want to find its derivative at this point here, x equals 10. So remember, when we're finding the derivative, visually we're finding the slope of the tangent line. So we've got some kind of a curve here. We want the slope of the tangent line at over here at x equals 10. Or if you want to think applied, what we're finding is given a relationship, and here's the description of that relationship, we're finding how fast the relationship changes when we're at x equals 10. So when the input is 10, if we increase that by 1 from 10 to 11, the derivative will tell us an approximate change, increase or decrease, in the function value itself. We've got a quotient. Let's use the quotient rule. So here's the template, right? Bottom times the derivative of the top minus the top times the derivative of the bottom. All of that over the bottom squared. Let's give it a go here. F prime of x is going to be, all right, the bottom, which is that 5x minus 2 factor, times the derivative of the top, which is 4, minus the top, 4x minus 3, times the derivative of the bottom, which is the 5, all over the bottom squared. So it's that 5x minus 2. We're going to square that. There's the calculus part. Now, let's see if we can simplify this using some algebra. So let's multiply through, right, distribute. So we will get f prime of x equals, over here we'll get 20x minus 8. 20x minus 8. And then here, now it's going to be a negative 5. Negative 5 times 4 is minus 20x. And then minus the negative is plus 15, all over that 5x minus 2 squared. And because we have a linear over a linear, you'll notice that 20x minus 20x goes out. That's always going to happen if you have a linear over a linear. So here's where we are now. We are at f prime of x equals, all right, we've got negative 8 and a 15. That's going to put us at 7 over that 5x minus 2. All right, here's our derivative. And we want f prime of x evaluated at x equals 10. Remember this notation? We used it in a few problems back, but the notation is you write your derivative or whatever expression you want, evaluated at that particular x value. So let's just write our derivative here, which is 7 over 5x minus 2 evaluated at x equals 10. So we'll put a 10 right in here. I'll do it up here, okay, up top right. So we'll get 7 over, now I don't need the parenthesis, oh we do, well, that's a squared there, right? I'm losing the square. All right, so we're going to get 5 times 10 minus 2 squared. We're going to get 7 over, now what do we have here? This is 50 minus 2 is 48 squared. 48 squared, I did that on my calculator. I'm going to get 2304. Okay, so there's our derivative. So I'm going to say now f prime of 10 is 7 over 2304. And I think I've got it right, so I'm going to claim now that that is our derivative. And what this means is that for this function right up here, okay, I'm up at the top, if we were to draw this function and go to x equals 10 and follow it to the curve, that the slope would be 7 over 2304. So essentially what it means is this is the slope of that tangent line. So if we're at 10 and we go to 11, right, 10 over to 11, well actually let's do it this way. If we were at 10 and went to 11, this would go, we'd go up by this much. It's a little hard to see. If I change that to a decimal, just to get a feel for this, right? So this is going to be 7 divided by 2304. I'm getting this. If I do change it, I'm going to get, this is 0.00300, say. So if we go from 10 to 11, this function would go up by only that much, not very much. Or we could think of it this way. If we're at 10 and we go over this much here, go over 2304, right? So we go way over 2304 04 units, how far would we go up? We'd go up 7.